Section 4.1, antiderivatives or antiderivatives, whichever way you prefer to say that. Well, we've spent all that time finding the derivative of a function. Let's see if we can't reverse the process to where if I know the derivative, we can find the original function. Now, notation, there's a couple of different notations we're going to use here. Initially, I'm going to say, okay, if I know the derivative of a function, or our derivative function, which we're going to call little f, we're going to call the original function capital F. So that little f is the derivative of cap f. Right? So the idea here is, well, if we know that what the derivative is, can I find the original function? So definition, we have a function cap f is called an antiderivative of little f if cap f prime of x is little f. All right, so watch your notation. That could be a little tricky, and then we're going to bring in some new different notations later. So if we consider the function little f of x equals 3x squared, we want to find its antiderivative. So the question there is, what is 3x squared the derivative of? Right. Well, cap f of x equals x cubed. If we differentiate that function, cap f prime of x is 3x squared. So since the derivative of x cubed is 3x squared, then that makes x cubed the antiderivative of 3x squared. But notice, if I let cap f of x be x cubed plus 4, the derivative of x cubed plus 4 is still 3x squared. If I let cap f of x be x cubed minus 5, the derivative of cap f of x there, x cubed minus 5, is still 3x squared. So in other words, you have all these different functions that actually all have the same derivative, 3x squared. And so if we reverse the process and we talk about the antiderivative of 3x squared, well, it could be x cubed, or it could be x cubed plus or minus some constant number, some constant value. So for a given function, there's actually an infinite number of antiderivatives. And you have to take that into account, keep that in mind when you're finding the antiderivative of a function. But the only difference between each of those antiderivatives is a constant. So that leads us to this theorem that says, if f of x is an antiderivative of a little f of x, then the most general antiderivative of little f is that function cap f plus a constant. So cap f of x plus c, where c is going to represent some arbitrary constant. So anytime you're finding an antiderivative, if it is a general antiderivative, and we'll talk about specific antiderivatives later, but we need more information for that. So here we're just finding what's called the general antiderivative, always tacking on that plus c. If without it, you're only finding one antiderivative of an infinite number. Now, the more formal notation that we use to represent that, or this whole process of finding an antiderivative, is what we call an integral, or integration is the process. If cap f is an antiderivative of little f, we write that the integral of little f of x dx is cap f of x plus c. This is called an indefinite integral. It's integral notation, represents the process of integration or integrating, which is finding an antiderivative. Right? So it's one and the same, it's just different language. This symbol is called an integral sign. It's a big elongated S, and there's a reason for it that we'll talk about later. For now, just take it for what it is. It represents the process of finding an antiderivative. It's the integration process. And a little f of x is called your integrand within your integral. And then there's also that little dx notation. This indicates to us the variable of integration, right? What are you integrating with respect to? Remember when we find derivatives? You know, we take a function y equals and we find the derivative dy dx. We always talked about using, or what is the variable that you're differentiating with respect to, and that's what the dx would tell you. So it's the change in y over change in x. Well, same thing here. If I'm integrating, I'm finding the antiderivative of a function. What am I finding the antiderivative with respect to? What variable? So the use of that dx. There are some rules for integration, rules for finding antiderivatives of certain types of functions. We've worked, these are focusing obviously on the types of functions that we've worked with up to this point. Certainly there are other types of functions and there are other processes that are used to find antiderivatives, but these are focusing on the ones that are relevant to the type of functions that we've been working with, right? So we're finding an antiderivative. Some people say we're anti-differentiating, or the process of anti-differentiation. I'd rather just say that we're integrating. Right? We're finding the antiderivative. We're finding the integral of our function. First, we've got a power rule. Remember, with differentiation, there's a power rule, a power function, x to the p, that if I differentiate, I multiply by the exponent, and then we would decrease the exponent by 1. Well, for anti-differentiation, if I'm going to reverse the process, let's increase the exponent by 1 and divide by the new exponent. So the integral of x to the p dx, where p is a constant, is x to the p plus 1 divided by p plus 1 plus c. Always tack on the plus c. Without it, you've left off all of your antiderivatives except 1. Now this power rule, notice, is only going to work as long as p is not equal to negative 1. Because if p was negative 1, if I had x to the negative 1 power, if you increase that by 1, you're going to get 0. And then you divide by 0, well, that's undefined. So the power rule works as long as your exponent is not negative 1. We'll address that here in a second. Number 2, we've got the integral of a constant. Excuse me. The integral of a constant. Let that constant be represented by k. The integral of k dx is k times x plus c. Because again, if you look at the derivative of k times x is simply k. It's the constant, right? The derivative of 2x is 2. So the antiderivative of 2 would be 2x plus c. Number 3, there is a constant multiple rule. The integral of a constant times a function is equal to the constant times the integral of the function. So in other words, if I have a integrand that contains a constant factor, I can pull that constant out of the integral. And it just makes working with the integral a little bit easier, working with the integrand. Right? So now I can find the antiderivative of our function and then just multiply that by the constant. So that's the main usefulness of that rule. It just makes it a little bit easier to work with your integrand. Number 4, we've talked about exponential functions, at least those base e, our natural exponential function. Now, if you remember, the derivative of e to the x was e to the x. So that makes the antiderivative of e to the x e to the x as well. And again, it's the nice thing about e to the x, it's its own derivative, which means it's also its own antiderivative. Now, when we were differentiating something of this form, let's say the derivative d dx of e to the kx. Remember, the derivative here is our function, and then chain rule said we then had to multiply by that constant, right? So it's k times e to the kx. Well, if we're going to find the antiderivative of a function of that form, again, we're just going to take it in the opposite direction. Instead of multiplying by k, we're going to divide by k. Or we could say multiply by its reciprocal. That's the more precise method. But either way is fine. So the integral of e to the kx dx is 1 over k times e to the kx plus c, or it's e to the kx divided by k plus c. And again, you could write that either way. That's personal preference. So divide by k or multiply by the reciprocal, either way. Then we get to our log functions, right? We worked with natural log functions, log base e. again. Now this is the integral of 1 over x, which brings us back to number 1. That's our power rule, or our power function, where p is -1, right? Because 1 over x is x to the -1. So if p is -1, I get 1 over x. But we said that wouldn't work with our power rule, because if we increase the exponent by 1, we get 0. Divide by 0, you're undefined. So power rule doesn't work here. But here's where we have to rely upon our previous experience. I know that the derivative of ln of x is 1 over x. Okay? So that means the antiderivative of 1 over x is ln of x plus c. But notice here we're not just saying ln of x, we're saying ln of the absolute value of x. Now this goes back a little bit. Here's a quick review. Domain of ln of x. The domain of the natural log function, or any log function, we said the argument has to be positive. So x has to be greater than 0 in this case. But what if we find the derivative of ln of the opposite of x? If we follow our chain rule, which says the derivative of ln of opposite of x, the derivative of a natural log function, was 1 over the argument times, see if I can squeeze this in over here, the derivative of the argument, which is -1. But then that gives us -1 over that negative x. That's still going to give me 1 over x as the derivative, right? But I can't have a negative number here, because the domain of our log functions is strictly positive, or at least the argument has to be positive. But what this does allow us to do, it allows us to address situations where x is negative in 1 over x. So I'm not limited by with the value of x in this case. Here, x could be positive or negative, and the antiderivative is still natural log of whatever x is, but we have to put on the absolute value because we know that argument cannot be negative. Right? So that's the song and dance as far as why this is what it is. For our purposes, it's just sufficient that you know that the antiderivative of 1 over x is natural log of the absolute value of x, not just ln of x, plus c. And if you leave off the absolute value, then again, you've left off half your functions. Okay? So, yeah, that's why it is not important for our purposes. Main thing is that I know what the antiderivative is. Number 6, there's a sum and difference rule. This is pretty straightforward in terms of if I have the integral of f of x plus or minus g of x, then that is equal to the integral of f of x plus, or it should be also a minus there, integral of g of x. So in other words, what this allows us to do is if I'm integrating a function that has multiple terms, where f and g represent the terms of the function, it allows you to integrate term by term, basically is what that does. Right? Now, whether or not you actually formally rewrite the thing this way is not absolutely necessary, and I'll show you in the examples. You can simply integrate term by term, and that would be sufficient. Right? But I'll point that out to you in the examples. Now, notice though that there's not a product and quotient rule here. Right? So the integral of a sum is equal to the sum of the integrals. The integral of a difference is equal to the difference of the integrals. That's not true for products and quotients. The integral of a product is not equal to the product of the integrals, and likewise with quotients. And that should make sense because remember, with differentiation, when we differentiate a sum, we can differentiate term by term, right? That's basically what we do. We differentiate each term of our function. But when we differentiate a product, there's a whole product rule involved, right? When we differentiate a quotient, there's a whole quotient rule involved. So I think it makes sense that if you reverse the process and you're looking at the antiderivative of a product or the antiderivative of a quotient, there's going to be a lot more to it. Okay, so be careful there. Now, Like I said, for our purposes, this is going to be sufficient. Right? But broader application of this stuff, it does not work for products and quotients. So for example, let's find a few antiderivatives. Right? So anti-differentiate or find the antiderivative, or we would say integrate the function. So number one, f of x equals 3x to the fourth, right? Power function. And like we're doing with when we differentiate, it's what type of function do you have? So what process or what rule do you follow for finding its antiderivative? So 3x to the fourth is a basic power function. It's the integral of 3x to the fourth. I'm going to increase the exponent by 1 and divide by the new exponent. Now notice again, the constant 3 doesn't really come into play. I could just as easily write this, if I could squeeze this in here, as 3 times the integral of x to the fourth dx, right? So that's that constant multiple rule, that if you have the integral of a constant times a function, I can rewrite that as the constant times the integral of the function, and then I integrate the function normally. So either way, you get 3x to the fifth over 5 plus c, or you could write that as 3/5 x to the fifth plus c. And again, that's just personal preference. Whichever way you care to write that, that's your choice. Either way is fine. Number two, f of x is the constant 4, right? That was our constant rule. We said the integral of a constant is the constant times x. So the integral of 4 dx is 4x plus c. Always a plus c. And while I keep emphasizing the plus c, let me also emphasize this dx. Because notice, every integral has a dx. Every single integral has a dx, or a d whatever your variable happens to be. It doesn't always have to be x. Right? Our functions can have different variables. But without that dx, if you just wrote the integral of 4, that means nothing. All right? So that's just as bad as leaving off the plus c once you do actually find the antiderivative. So make sure you're including dx in your integrals. And then make sure you're including plus c when you're finding a general antiderivative. Number three, cap f of x equals 2 plus x squared minus 6x to the fifth. There again, that's just our sum and difference rule applied. I said, I'm not going to write that out as we wrote it up here, where we broke it up and said, okay, I'd have to break it up and take the integral of each of our terms. We can just simply find the antiderivative term by term, just like when we differentiate. So the antiderivative of 2 plus x squared minus 6x to the fifth would be the antiderivative of 2, which is 2x. The antiderivative of x squared, which would be x cubed over 3, right, increased by 1 and divide, minus 6x to the sixth over 6, increase the exponent by 1 and divide, plus c. And then we're able to simplify the 6 over 6 to 1, so I end up with 2x plus 1/5 x cubed minus x to the sixth plus c as our general antiderivative. Number four, we got f of x equals e to the x, and this is what we had mentioned earlier, so I wanted to formally state that again. If our function f of x is e to the x, the integral of e to the x is also e to the x, right? Plus c. It's its own derivative, it's its own antiderivative. But then here's that rule that we outlined earlier. F of x equals 3e to the 2x. The integral of 3e to the 2x, again, the constant 3 doesn't affect anything. I can look at that as a constant factor. So I'm finding the antiderivative of e to the 2x, which would be e to the 2x times the reciprocal of the constant. Or we said we divide by the constant. So the antiderivative of 3e to the 2x is 3e to the 2x divided by 2, or times 1/2, plus c. Number six, there's recognize our natural log function. Right? So again, I have to recognize that because power rule doesn't work. I can't just do x to the -1 and then do the power rule. So f of x equals 5 over x. I would say that the integral of 5 over x dx, and for whatever reason I wrote that one as 5 times the integral of 1 over x. Right? So again, emphasizing that constant multiple rule. And then our integral of 1 over x is natural log of the absolute value of x. So 5 times that, plus c. All right, so those are pretty basic. Now, the next few kind of illustrate broader application of some of these rules, mainly power rule for our purposes. In that, we talked about this with when we were differentiating as well. If I have a function that I can't directly find the derivative of, maybe if I put it into a different form or write it into a different format, I can apply one of the rules or processes that we had for differentiating. Well, the same is true for integration as well. All right. So number 7, f of x equals cube root of x, well, there's nothing I can do with that as written. But if I write it as x to the 1/3, there's our power function, and I can integrate a power function using our power rule. Now, you do have to play with your fractions again, so be careful. Am I finding the derivative or am I finding the antiderivative? Which way do I go with the calculation? So antiderivative says I increase the exponent, so 1/3 plus 1 would give you 4/3. And then we said divide by the new exponent, which so I'm dividing by 4/3. So I get x to the 4/3 divided by 4/3. Now I don't want to leave it that way. Take the extra step. Dividing by 4/3 means multiplying by 3/4. So our most general antiderivative would be 3/4 x to the 4/3 plus c. Always plus c. Number 8, if f of x equals 1 over x cubed. All right, now again, noticing that, I can work with that function in terms of an antiderivative if I put it in the form of our power function, rewrite that as x to the -3. Right? I mean, these are all the same things we did when we were finding derivatives using power rule. So we're going to do the same thing when we find the antiderivative. So I write it as a power function, x to the -3, and then we follow our power rule. I say the integral of x to the -3 dx. Now be careful on the negative side. I see a lot of mistakes made here all the time because the rule is for antiderivatives, we're going to increase the exponent by 1. And if I increase -3 by 1, I get -2. All right, so be careful. Don't go the wrong way with that. And then we divide by the new exponent, so divided by -2 plus c. So I could then rewrite that, say, as -1/2 times x to the -2 plus c, or if you want to drop that x to the denominator to make the exponent positive, and there should be a negative in front of that as well. -1 over 2x squared plus c. All right. And again, which way we write that, with the x to the -2 or the 1 over 2x squared, either way is fine. Just be careful on my math lab as always. Number 9, I've got f of x equals x squared minus 7x plus 2 all over x squared. There's a fraction. And again, this is the same thing we did when we were differentiating. With derivatives, though, you could use quotient rule there if you wanted to. But we said an easier way to do it was to break the fraction up and then differentiate term by term. So we don't have a choice here. That's how we're going to have to do it. So it's the same thing that we did when we were finding derivatives. I take the fraction and I take each of the terms in the numerator over the denominator. So I can rewrite that as x squared over x squared minus 7x over x squared plus 2 over x squared. Simplify or write in terms of a power function. Now notice I've got a couple of different functions involved here. I mean, x squared over x squared is 1. That's no problem there. 7x over x squared simplifies to 7 over x. And then I've got the 2 over x squared. Now notice I'm rewriting the 2 over x squared as 2x to the -2. Not what I wanted. But I left this as 7 over x. And that's simply because of the type of function. We know that the antiderivative, and there's a 1, the antiderivative of 7 over x, that's going to be our natural log function. Whereas the 2 over x squared, I'm going to have to use power rule. So you have to recognize those are two different types of functions, or at least two different rules that you're using to find their antiderivatives. So then I'm looking at the integral of 1 minus 7 over x plus 2x to the -2 dx. The antiderivative of 1 is x. The antiderivative of 7 over x would be 7 times natural log of the absolute value of x. And then our antiderivative of 2x to the -2, again, we're increasing the exponent by 1, so that'd be 2x to the -1 over -1. which would make that negative 2x to the negative 1, or negative 2 over x. So x minus 7 natural log of absolute value of x minus 2 over x plus c, plus c, plus c, plus c. Now, all of these are indefinite integrals, right? We always had to tack on that arbitrary constant because you had an infinite number of functions who all had the same derivative. And that's because the derivative of the constant is 0. So regardless of what that constant was, when you differentiate the constant, the derivative is 0 and it's gone. Now, if we are given more information, if we have enough information though, we can find that constant under specific conditions. So we call these initial conditions if we're given information about cap f of x, our antiderivative, then we may be able to find the value for c and give the specific antiderivative, cap f of x. So for example, given that little f of x is x cubed plus 5x, but then also told that cap f of 0 is 1, right? So we're given a specific piece of information about our antiderivative cap f. We can find the specific antiderivative cap f of x. So we do the same process for the antiderivative, right? Our general antiderivative, that's just, again, our power rules. So increase the exponent by 1 and divide. So I've got x to the 4th over 4 plus 5x squared over 2. And then we tack on our constant c. And there's our general antiderivative. But then we're given information about cap f. We know that cap f of 0. So I'm just going to plug 0 into cap f that we just found. 0 to the 4th over 4 plus 5 times 0 squared over 2 plus c. We're told that that's equal to 1. And now what I've got is an equation that I can solve for c. Right? So that'll give us 0 plus 0 plus c equals 1, which means c equals 1 in this case. And then once you find your c value, then you can go back to your general antiderivative and simply plug it in. So our specific antiderivative in this case for cap f of x is x to the 4th over 4 plus 5x squared over 2 plus 1. Right? So yeah, if you're given specific information about your antiderivative, then you can find the c value, and then you just tack that on in place of c. And that is a specific antiderivative. Now, other notations, because like I said earlier, the notations that you use for the derivative or the antiderivative, I mean, it's arbitrary, with respect to the functions involved. In other words, so far we've been using little f as the derivative and cap f as the antiderivative. So we would say the integral of little f is cap f plus c. Well, we could just as easily say that little f is our function and f prime is our derivative, right? I mean, that's our notation that we've used previously. And so if we use that notation, then I could say that the integral of f prime is little f of x plus c, right? Because that would be the antiderivative of f prime. So you're going to see both ways done, both notations used. So whether I use cap f for our function and little f as the derivative, which makes cap f the antiderivative, or we use little f for our function and f prime as our derivative, which makes little f the antiderivative. And so it's just all relevant to whatever notation you're using. So for example, if we let f prime of x be the function e to the negative 3x, then the function little f of x would be the integral of e to the negative 3x, and there's our antiderivative of e to the kx, which is e to the kx divided by k or times 1 over k. So I get negative 1/3 e to the negative 3x plus c. All right, applications, we always have applications with this stuff. Again, there's a lot of real-world applications, not just for derivatives, but antiderivatives. So for this one, we have an arrow that's shot directly upward from a height of 6 feet above the ground, has a velocity that is modeled by the function v of t equals negative 32t plus 125 feet per second. So this is the velocity of our arrow that's shot upward at a height of 6 feet above the ground. F is a number, or F, where T, excuse me, is the number of seconds after the arrow was shot. Our question, let's find the arrow's height and velocity after 5 seconds. Now, recall, we did some applications with, remember, position and velocity and acceleration. We talked about those guys, where velocity was the derivative of our position function, and then acceleration was our second derivative. Well, here our position function is the height, so I'm going to call it a height function, so we'll call it h of t. So our position function is our height function, which is h of t, which means the derivative h prime is your velocity function, right? The derivative of your position function is your velocity function. So that makes h the antiderivative of v. So the integral of your velocity function is your position function, which is h in this case, plus c. Right? So if I'm looking for the height and the velocity of our arrow, well, I have the velocity function, that's not an issue, but I need the height function. So what is the height of our arrow? Well, the height of the arrow, h of t, is the integral of our velocity function, which is negative 32t plus 125. And that's, again, a nice little power function, so I'm just going to use power rule, negative 32t squared over 2 increased by 1 and divide, plus the antiderivative of our constant 125 would be 125t plus c. There's our arbitrary constant. So h of t, simplifying, I've got negative 16t squared plus 125t plus c. Now I do know the initial height of our arrow, right? Because remember in our problem it told us that the arrow was shot upwards from a height of 6 feet. Well, that would be the initial height. That's when t is 0, right? So I can use that information to find c in this case, because we know the height at time t equals 0 is 6 feet. So I'm just plugging 0 into our height function that we just found, setting it equal to 6. And again, that's going to zero out those first couple of terms. It just leaves me with c equals 6. So I get our height function h of t of negative 16t squared plus 125 plus 6. Notice again, that was our initial condition, right? That was our initial height where t equals 0 or x equals 0, right? In general notation. And then we can evaluate each of those functions, right? So the answering the question is the easy part. It's just you have to, use your antiderivative process to find the height function. So the height after 5 seconds, h of 5 is 231 feet if you plug 5 into that height function. Now, if you plug 5 into velocity, v of 5, you actually get negative 35 feet per second. Now, that's just using, again, the velocity function that we were given initially, right, the negative 32t plus 125. Now, what does it mean for the velocity to be negative? Now, remember, the velocity is the derivative of your height. So it gives you the rate of change in the height function. Remember, that's what your derivative tells you. So the fact that the velocity is negative means that your height is what? It's decreasing, right? Remember, a positive derivative means the function is increasing, and negative derivative means the function is decreasing. So in this context, a positive velocity would mean that the arrow is going up, the height is increasing. A negative velocity means that the arrow is coming down because its height is decreasing, right? So the arrow is falling. Yeah, so there's direction components now. So it's not just all about the values that you find, but what do they actually tell you in the context of your problem. Number 2, let's find a company's total cost function if we know the marginal cost function. We've done a lot of that with taking our cost, finding the marginal cost, which remember the marginal cost is your derivative. It's the rate of change in your cost. So if we know the marginal cost function, c prime, in this case 5x squared minus 7x plus 4, We're also given that the cost of producing 6 units of our item is $260. So we've got our marginal cost, we've got C prime, and we've got a specific cost for 6 items. So then our function C, our cost function, is the antiderivative, it's the integral of our derivative, of our marginal cost. So C of x is the integral of C prime of x. So it's the integral of our C prime, which we're given, 5x squared minus 7x plus 4 dx. So then C of x, using our power rule, I've got 5x cubed over 3 minus 7x squared over 2 plus our antiderivative of the constant is 4x plus C, general antiderivative. And then using the specific information that we're given, we're told that the cost of producing 6 units is $260. So cost function evaluated at x equals 6, plugging 6 in is equal to $60, and then solving for C. Right? So we got a few little calculations in this one. I ended up with 360 minus 126 plus 24 plus C. 258 plus C equals 260 to subtract 258, and we get C equals 2 in this case. So here is our specific cost function for this model. 5x cubed over 3 minus 7x squared over 2 plus 4x plus 2. Find a company's total cost function if its marginal cost is given by C prime. So there's again another marginal cost function, 16x minus 8 in this case. And we're also told that it has fixed costs of $13. All right, so this is really more about just language, making sure we're clear on the terminology. What does it mean for fixed costs? Right? Fixed costs are those costs that the company has before they produce their first item, right? Maybe you need a facility to manufacture the item. You need machinery maybe to manufacture the item, that kind of stuff. So there are fixed costs that have to be paid out before you manufacture your first item. So in other words, we could say that this is the cost for 0 units. That's our fixed costs. Right? Now numbers are small here, but that's the idea. So our cost function, C of x, again, is the integral of our derivative, C prime. It's the integral of our marginal cost. It's the antiderivative of 16x minus 8 dx. Using our power rule again, 16x squared over 2 minus 8x plus C, or 8x squared minus 8x plus C. And again, the initial costs, or fixed costs, would be our cost at time t equals 0, or before the first item is produced, when x equals 0. So again, fixed costs, C of 0. I'm just plugging that into our cost function, and of course we would get C equals 0. And that's because our cost function in this case is a polynomial. I mean, anytime you have a polynomial function and you plug 0 into that polynomial, all of your terms are going to zero out, right? And you're going to be left with C equals whatever that constant is. Right. But again, that's simply because the cost function in this case is a polynomial. That would not necessarily be true if that's not a polynomial. So don't fall into the trap of thinking it's just going to be a matter of adding 13 or adding that constant to it. It depends on the type of function. But in this case, that gives us a cost function of 8x squared minus 8x plus 13. Right. That is section 4.1.